I am going to finish this problem. So this problem that I'm going to work on, and I've already done most of the work, I just need to animate it. And the problem is, so you have a hoop, and it can rotate this way, and there's a bead on the hoop. And so we want to model the motion of that bead. So I'm going to go through the solution, even though I have a video with all the details. I'm going to go through the solution fast. And then, and I already solved this. I got an equation, a differential equation for the solution, and then I modeled the angle as a function of time. But I didn't animate it. So now I'm going to make an animation in VPython, ClosesScript VPython, that shows the disk, the hoop rotating with the bead on there, and that's going to be great. And I did it already, so it shouldn't be too hard. I'm going to work through again from scratch. I might make some mistakes, but here we go. Okay, let me turn off this camera. Okay, so here's the situation. I have this hoop and I have a bead. Now, in this case, how do you solve a problem like this? You can't use Newtonian mechanics, because Newtonian mechanics says, hey, what's the forces acting on the object, and what's that acceleration due to those forces? So in this case, I have this weird equation of force of constraint, right? Because the bead can only move along the hoop, but the hoop's spinning too. So what forces does a hoop exert on the bead? You couldn't even, if this was a stationary hoop, you could say, well, I could find that normal force from the wire of the hoop using conservation of energy, but you can't, because energy is not conserved, because there's some driving force that makes that thing rotate. So you can't do that. I assume there is some way that you could. There probably is a way that you could calculate the constraint force, but it's just way too much work. So instead, we're going to use the Lagrangian mechanics. Lagrangian mechanics says that if I calculate the Lagrangian, which is the kinetic energy minus the potential, then the Euler-Lagrange equation finds the equations of motion. It's the principle of least action. It says that the action is this integral over space-time of the Lagrangian, and it's minimized, and this is the solution, where Q is some variable. And that's the key here, because we can choose any generalized coordinate that we want to describe this situation. And so the first thing we do is say, well, how many degrees of freedom are there? Well, in this case, there's only 1 degree of freedom, right? Because how many pieces of things can change? Well, although the hoop rotates in this direction, that's set, right? I know where that hoop is at any given time, so it's not a variable. The only variable is where along that hoop is the bead. So I can pick one single variable like theta. Theta would be my generalized coordinate. But then we have the problem of getting kinetic and potential energy in terms of the generalized coordinate theta, and that's the problem. So what we do is this right here is to say, okay, I can write the kinetic energy in terms of the Cartesian coordinates. I can write the potential energy in terms of the Cartesian coordinates. And in here we're using this dot notation. So x dot is the derivative of x with respect to time. So this is the velocity in the x direction, the velocity in the y direction, the velocity in the z direction. I have to square all those and add them together. But if I get a relationship between the Cartesian coordinates and the generalized coordinate, I can do this. So if I look at this and I call this my y direction, then my y value just depends on the angle theta. It doesn't depend on how this disk is rotated. So y is just going to be negative r cosine theta. The x and the z components depend on both theta and how far this thing's rotated, right? So I have r sine theta is the projection onto this xz plane, and then I have to multiply by sine omega t to find out exactly where it is. And then so do the same thing for z, except it's cosine omega t. So now I have these functions, and I can go ahead and plug in my y value up here into potential to get that in terms of theta. Okay. And then to get these, I have to get the kinetic energy, I have to take the derivative with respect to time of x, y, and z, square them and add them together, and that's where the mess happens. Did I skip a page? I thought I worked all this out. Let's see. Maybe these are backwards. Yeah, this is it right here. So here's my y. Actually, there should be a negative. It doesn't matter. It comes out. Yeah, y was negative r cosine theta. So y dot, I take the derivative, and you do get a theta dot term in there. Remember, don't forget your product rule. And then I need to square that, and that's not so bad. And then I do the same thing for x. Now, when I take the derivative, I have a product rule. I have this term, and I have that term. So I have two terms. So I have to take the derivative of this times that plus the derivative of this times that. But both of these have to use the chain rule because they have a term inside of them. So this term, if I take the derivative, I get the derivative of theta is theta dot. And remember, the dot notation means derivative with respect to time. And then the cosine term, that's from this, right? And then I have to multiply by sine. And then I take the derivative of this, which is going to be cosine omega t, but then I have to take the derivative of omega t, and I get omega. But now that I have two terms, I have to square that, and I get a mess, right? I get three terms. I get this squared, and then the cross term. Now I do the same thing for z, and I get three terms. But you'll notice here that there's a negative sign in the z derivative. And so when I get my cross term, it's going to be the exact same cross term as up here, but negative, and those cancel. And then I get a bunch of sine squares and cosine squares, and those all factor out so that I can get my kinetic energy, which I'm going to link the video to this down below. There. So I get all of this x squared plus y squared plus z squared is going to be this right here. R squared theta dot squared plus r squared omega squared sine squared theta. And then I can use the Euler-Lagrange equation. Then I can get my Lagrangian right here. So it's the kinetic energy, T, so it's 1/2 m times all that, minus the potential, which is going to be plus mgr cosine theta. Now, the Euler-Lagrange equation says I need to take the partial of L with respect to theta, and then the partial of L with respect to theta dot, and take the derivative with respect to time. So the partial of L with respect to theta isn't too bad. I look for what terms have theta in it. There's just that one right there. So I have to take the derivative of sine squared theta. It's going to be 2 sine theta. And then I have to take the derivative of sine theta, and that's going to be cosine theta. And that's how I get this term right here. I multiply by the 1/2. It's a partial, right? So I don't have to take the derivative of theta. Again, I took the derivative with respect to theta. And I assumed all other values are constant. And then over here, I have to take the partial of this with respect to theta, and I get negative mgr sine theta. For theta dot, there's only one term with theta dot in it. It's right there. So I bring down the power of 2, and I get 2/2 m r squared theta dot. Okay, and then I have to take the derivative of that with respect to time, and the only thing that changes with time is theta dot. So I get m r theta double dot, r squared theta double dot. And I put these two together, and that's it. Okay, I have my differential equation of motion, right? That's it. Now, this is not so simple to solve because the second derivative of theta depends on theta, right? So it's a non-trivial equation. I could, of course, cancel all the masses and stuff like that. So instead what I do, I have it right here. And again, I apologize for going over this rapidly, but I have a whole video on this. So I hope you'll watch that if you want all the details. Maybe you don't want the details. Maybe you're like, just give me the answer, dude, and that's fine. Okay. You really should work through this, though. Okay, so if I break this into small time steps, I can make the approximation that theta double dot's constant over that time interval. And so if I use that equation right up here, solving for theta double dot, I can calculate theta double dot. Now, theta double dot is equal to delta theta dot over delta t, right? It's the derivative with respect to theta, but if I assume things are constant over that time interval, then I can use this to calculate the change in theta dot. And so if I know that theta dot at the beginning of the time interval, theta 1 dot, I can find the theta at the end of the time interval, theta 2 dot. So that's where this equation comes right here. It says, break it into time steps of delta t. Assume theta double dot's constant. Take the starting theta dot 1, and then use that to get theta dot 2. Then I can do the same thing with theta dot. Now I'm going to assume theta dot's constant, and I can use that to solve for theta and theta 2, or the update theta 2. So now I can do the same idea, update theta, and then update time. And then just go back over. Now I have a new theta. I need to recalculate theta double dot and do the whole thing over again and again and again. If I use, and this is the Euler method. if I use delta t equals 0.01 seconds, which I actually use smaller than that, then I would have to do 100 of these loops just to get 1 second of data. And I don't want to do that. You don't want to do that. And that's why we use Python. Okay, so I'm going to show you the code I use to calculate this. It's the code that I did in that program. And then I'm going to copy that code and use it to animate what I want to animate. Okay. So this is the code that I got, and you'll notice I decided to put my little picture up at the top. I just feel like it works better up there. Okay, so let me just go through the key things. It is a numerical calculation, and that means I have to use numbers. I can't say, oh, it's just R. I have to pick an actual value for R. So I have a 5 centimeter radius. W is my angular velocity of 20 radians per second. I just pick these numbers. M is the mass of the bead, which never comes in there. Then here's my starting angle theta, and I like to think in terms of degrees, so I converted it to radians. Now I do need the initial theta dot. I picked 0. You can pick whatever you want. I need the value for g, time step. Okay, theta. This is right here, line 12. I'm going to take this out in just a second. Actually, let's take this out now. I'm just going to comment this out. Let me copy this first. So let's just make a copy of this. Let's see. Update view on trinket. Okay, then copy it. Okay, let's see. 3D model of rotating hoop and bead. Save. Okay, so this, I'm going to take this line. Oh, save. It didn't save it. I don't know why it has trouble doing this sometimes. Let's just run it first. So I'm going to take this line 12 out. I'm going to comment that out. Let's see if I save it now. No? Run it. Save it. Save. There it goes. Weird. Okay. So now let's go through the thing. Line 13 is just sets up the graph. Line 14 is part of line 13. There's a comma in there. And then F1 is line 15 is the function that plots it. Okay, that's my actual curve. Now down here, I just run this for 5 seconds, so while t is less than 5. Line 19, I just calculate theta double dot. That's all I did. Line 20, I update theta dot. And line 21, I update theta. And that's it. And then I plot t and theta, and I convert theta back into degrees, and so you can see what it looks like. So the bead just oscillates up and down in the angle, but the whole thing's rotating around too. Now in line 12, I wasn't sure about my solution, so what I did was I said, what angle of theta would produce a stable orbit, right, where it wouldn't slide up or down the hoop? And so you can just say, if it's not sliding up or down the hoop, you can use Newtonian mechanics. I can calculate that normal force, and then since it stays in a circular path, and then once I find that angle theta, I put it at that, and it should stay at that same theta. So if I comment this out, and I calculated that, and that's my value for theta for a stable orbit, and then I run it, and then you see that the angle doesn't change. So it did work, so I felt good about that. It made me happy. It made me feel good, right? And that's important in Python programming. You have to feel good, which is not true. I just made that up. But I do like to feel good when things run. That does make me happy. Okay, so we have this thing working. Now we want to model it. Okay, so that's the power in Python, is it also has these models. So let's just go ahead and make our hoop. And it's a 3D object. So I'm gonna start off with this hoop. I'm gonna say hoop equals ring. Okay, so let's just go over here to GlowScript and go to help, just so you know where to find these things. And choose 3D object, ring. So these objects are built in, and it tells you everything you need to know about it. And look right here, I have some properties. The position is the location of the center. Axis is a vector, that vector, or the axis of rotation, or whatever you want to call it. And then we have the radius. Oh, the radius. Oh, no, that's right. The radius goes to the middle. Okay. So it's a ring. I need to give it a position. So let's say it's at the origin, vector 0, 0, 0. I need the axis. So in Python, the y direction is up, the x is this way, and z is out. So I want the axis. I want to start with it like that. So I'm going to have the axis of axis equals vector 0, 0, 1 in the z direction. The radius is r. Now the thickness. Let's just put that down here. The thickness, I have to pick. Let's say it's r over 20. Let's just try that. Okay, let's run this and see what it looks like. See, now in Python, it's a 3D environment there. I can rotate around. It's not rotate, there it goes. And I can zoom in and out. And you could change the lighting and the texture and all that stuff, but I don't really need to. And I think that's a little thick. It's supposed to be a wire. So how about r divided by 30? Here we're in the art stage of physics, right? I want it a little bit smaller. Okay, now I'm going to put my bead on there. But before I do that, I want to, how do you rotate this whole thing? Okay, how do I make it animate and rotate? So if I change that axis vector, then it will rotate, right? If I just change it each time. So let's just try this. Down in my loop, before update time, I'm going to say this. Hoop dot axis equals vector. So I want to change the x and z components. I don't want to change the y component of the axis. So let's just say this: cosine omega times t, 0 sine omega times t. All right. So in each step, I'm just changing the axis. And let's see, at t equals 0, then cosine. This would be wrong. Right, because at t equals 0, it would be it'd be like this, because I'd have cosine as 1 and sine as 0. So let's actually put this at cosine and sine. And let's just, okay, now there's another thing. If I want to animate this motion, then I have to tell Python how fast to move things. It's going to go as fast as it can, unless I tell it, hey, slow the heck down, man. So let's do that. I can go up here into my loop and put rate of 1,000. Now, this says don't do any more than 1,000 loops per second. And I have a time step of 1/1000th of a second. So that would be real time. Okay. Now, I think that might be a little fast. 20 radians per second is a little fast, but let's just do it anyway. That looks pretty cool. It's going to run for 5 seconds. And I'm just looking at it from different angles. That's cool. You got to admit that's cool. Okay. Let's just run this a little bit slower. Let's run this for 1 second, and let's do it at 10th speed. Okay, and you notice there the camera zoomed out just so it could handle the rotations. And so it's rotating this way. Okay. Actually, I think in my problem I have it rotate the other way. So if I want to rotate it the other way, then I can just change the sign of this. Negative and negative. It is, I can't even tell which way it's rotating now. Actually, I could look it from above. No, I had it right the other way. It was an optical illusion. Okay. No. Okay, I have to change one of them to be negative. Now it's rotating the way I like it. Okay, that's the way I had it in my mind in the other case. Now we can go ahead and add our bead on there. So let's make another object called bead. You need to make it what it is, right? And let's just make this a sphere. So sphere is an object built into Python, and it has some properties. So let's say the position is the position of the sphere, and that's going to be, okay. Now I can go back to my, GlowScript is like a Cartesian system, right? it has the vectors in x, y, z coordinates. So if I have the x, y, z coordinate of the bead, then I can just put that in here, and that's going to help it out a lot. So I'm looking back over here at my paper, and I solved for x, y, and z. I just need to find that again. Where'd it go? Here it is. Okay, so I know x, y, and z. I can just use those coordinates and put it in here. So the position is going to be vector. They all have an r in there, so I'm going to factor that r out. R times the x coordinate, which is sine of theta, times sine of omega times t. Oops. The y. Which I lost. That's. Okay, that's right. The y coordinate is going to be negative cosine theta. And the z coordinate is going to be sine theta times cosine omega t. And that's the end of that. Now I need the radius. Let's just put this on the next line. The radius is going to be equal to, let's see, the radius of the wire was r divided by 40. So let's say r divided by 30 and see what that looks like. And we can give it a color. Color equals color dot yellow. And let's also have it leave a trail behind, because that will be really cool looking. So let's say make trail equals true. And that's in the GlowScript documentation. You can make a trail for something like that. Now let's just run that and see if it looks fine. It won't move, right? Because we never told it to move. And see, good thing we ran it. Can't find WT because it doesn't exist, dummy. W times T. Okay. It's okay to make mistakes. Okay, there you go. So you'll notice that the bead stays there, and it's also a little too small. See, good thing we ran it. Okay, so let's make it r divided by 20. That looks good. It's a little small still, but r divided by, that's fine. Okay, so now what do? Now we go down here, and I need to update the position of the bead. So let's say bead, not bread, bead.pos equals, and it's just the same thing. But now T changes, everything changes, so this will update it. But I have to tell it to do that. Do I have it right? I think that's right. Okay. And they're going in opposite directions. Okay. So that's not cool. So actually, I guess I have to rotate this in the other way. So down here, minus, let's change this to just positive. Okay, now the problem is that they're out of phase, right? So I use cosine and sine, but the axis of this vector is perpendicular to that. So I actually need to switch sine and cosine for my hoop. So down here, I will put this as cosine, and this is sine. Let's see if that does it. No. Now they're going backwards. Okay, now I need that negative sign. The negative. Aha, got it. Okay, now remember I left in there my coordinates for a stable orbit, and you can see that it is indeed stable. Okay, so let's go ahead and put it at some other angle. And this is running in slow motion, right? Because I'm at 1/10 speed. Okay, so let's go over here and just comment out this line, and it'll start at a 45-degree angle. Okay, I don't know. That's a little too slow. Let's run this at half speed. I mean, is it working? I guess it's working. I mean, I don't really know for sure. It looks cool. It looks like it's working. Let's run this for 5 seconds. I mean, it worked with the other case, so I mean, it's pretty. I like it. Let's give it what? Let's see. Theta is 45. What if I started up high? What if I started at theta as like 110? It should still work, right? Oh, look at that. Ooh. That's pretty cool. Okay, so I think I'm done here. Ooh, yeah, look at that. That's cool. You know, that's the thing I love about Python. You make these, especially when you include the trails. You just get this cool stuff. You know, it's just, you could hang this on your refrigerator or something. It's just neat. It's like that. Remember that screensaver pipes? That's what I think about. But it's actually, we know the physics behind this. You'll notice that there's some little jags in there. That's just the trail does that after a while. I think there's some errors in the drawing, but that's fine. Okay, so there you go. I went back through the equation of motion for a bead on a hoop, and I did everything I did before, plus make a 3-dimensional model of it, and that was really cool. I enjoyed it. Thanks for being here with me. I had fun with you, and we'll do something else later. That means I'll talk to you later.